This is a lesson on wave energy and intensity in the unit on simple harmonic motion in waves. In a prior lesson, I talked about properties of waves, and in this lesson, I am going to highlight that waves carry energy from point A to point B. So we are very interested in how to quantify that energy. How do I quantify that? With waves, we know that waves expand radially from their source. So if I put some source here, the wave will expand radially outward in 3 different dimensions. So the energy of that wave will be evenly distributed over the surface area of a sphere. So I put the surface area of a sphere down here. As the energy radiates outward, the sphere gets larger, and so that the same amount, that total energy, is distributed evenly over an ever-increasing surface area. So that's why when you move away from a source that is emitted waves, the received intensity goes down. How do we quantify that? Well, intensity is defined to be power over area. And remember, power is energy per unit time, or watts. So I'm going to take how much energy is being produced per unit time, and I'm going to normalize that over some surface area. You saw that on the previous slide. It depends on how big that area is that the energy is being distributed over. And I put a diagram over here for you to be able to see that. This is from Kutnell and Johnson, their 9th edition book. And when I look at this, and I'm going to go really easy here, I see 1, 2, 3, 4, 5 beams of sound here. And in the first situation, those 5 beams of sound are closer to the speaker, and so they're not going to be distributed over a large area. And so you will have a large intensity closer to the source. As it moves away, those 5 waves are extended over a larger surface area and the intensity goes down. You would also see that a surface area of the same as 1 would have a smaller amount of waves through it. I'm going to note that intensity is given as watts per meter squared, so power per unit area is watts per meter squared, and this is a scalar unit. Again, this is not vectors. Even though there's arrows here, it's to denote radially outward rather than a vector value. This is a scalar. Energy is always a scalar. The first problem I chose to exemplify the concepts is solar collector. The average intensity of sunlight on Earth's surface is about 700 watts per meter squared. Calculate the amount of energy that falls on a solar collector having an area of 0.5 meters squared in 8 hours. So maybe you have a solar collector and you left it out all day. How much energy was collected? When I think about the equations, I see energy in the equation for power, and power goes into intensity. So I can do that. Intensity is energy per unit time over area. And they're asking me to solve this equation for energy. How much energy, the amount of energy that falls on it. So I'm going to do that real quick. Let me simplify. Energy divided by time times area. So when I solve for energy, I get intensity times time times area. And I'm going to plug in those values. I get 700 watts per meter squared. Multiply by 8 hours. So I need 8 hours times 3,600 seconds per hour. And then the area they tell me is 0.5. When I run those numbers through the calculator, I get what looks like a lot of energy, 10,080,000 joules. I was interested in how much energy that was in a number that I recognized, and so I converted it to calories. Remember that 1 big C calorie is 4,186 joules, so I just divided by that number, and I got about 2,410 calories. So a big meal of food would result in 8 hours of this solar collector. And that's an application of that. The next problem is another application of intensity, cancer treatment with radiation. A laser beam is used to burn away cancerous tissue. When 90% of its intensity is absorbed, the laser puts 504 joules of energy into a circular spot 2 millimeters in diameter in 4 seconds. So they turn the laser beam on for 4 seconds. They know that 504 joules of energy went into a circular spot of 2 millimeters of diameter. And that's only 90% of the energy that they released there. So I'm going to put this down here. The energy absorbed was 90% of the energy total. And they don't tell me the energy total, but I would be able to find it. It says, what is the intensity of the laser beam? So that's why I was going to. We don't care what was actually absorbed. We care what came out originally. So we need to know what the total energy was. Intensity for part A will equal the energy per unit time divided by the area. When I solve for E total down here, I will get E absorbed divided by 0.9. So that's what I'm going to put up in the equation up here. E absorbed divided by 0.9. That's the total energy that came out. I will find the total intensity of that laser. Doing a little bit of algebra, I get the area on the bottom. The area I know is a circular spot, a diameter of 2 millimeters. So I'm going to put pi times the diameter divided by 2 squared, pi r squared. And then I also have time, which is also just given in the problem. I'm going to put numbers in there. So I total equals 504 divided by 0.9. On the bottom goes pi, 2 times 10 to the negative third divided by 2. Remember, millimeters just to the negative third power. I have to square the radius, and then the time is 4 seconds. And when I run this through the calculator, I get the total intensity to be actually pretty large. 44 million and some change here. And I'll write this all out. This is a decimal place here, 71 watts per meter squared. Huge. We expect that though. We're burning away cancerous tissue, so it has to be a really large intensity. It's a very small beam, so it's not going through a lot of the human tissue. So I was interested. It says, discuss how this intensity compares to the average intensity of sunlight, which we saw in the previous example, 700 watts per meter squared. Can you see that? The difference of this radiation used for cancer and just what we get on the surface of the earth from the sun is a lot different. This is super huge. I actually divided this by 700 because I wanted to know how many intensities of the sun this is. So I total is 63,662 times the intensity of the sun. Huge intensity here. It asks the implications it would have if the laser beam entered your eye. So we're already told not to stare at the sun. If we stare at the sun for a certain amount of time, don't stare at the sun too long, you're going to burn your eye. And here the laser has 64,000 times the intensity of the sun. And so any amount of time in your eye, that would burn the tissue in your eye as well. So that's why there's the warnings about don't look at a laser.